Hello and welcome. My name is Jerry and today I shall be teaching you projectile motion. Now, what is projectile motion? Projectile motion is basically the study of stuff we chuck into the air. For example, this cannonball that I've animated being shot out of a cannon. The aim of our analysis and the ultimate goal of our equation should be to be able to tell us where the ball will be in its flight path simply by our plugging in a given amount of time. For example, I should be able to plug into my equations 1.2 seconds and it should be able to tell me where the ball is in its flight path at that instant in time. My equations should also be able to tell me other important things about the path of the ball. For example, how high, what is the maximum height the ball will reach in its flight path? What is the range it will go before it lands? And other things like how much time it will take to travel the entire distance, and stuff like that. So, how are we going to attack this problem? This is a non-trivial problem, but at the core of the entire problem are two very trivial equations that I need you to be familiar with before we go on to understand the problem. The two equations I'm talking about are V is equal to U plus AT and S is equal to UT plus half AT squared. Some of you might already be familiar with these equations, having done them while studying simple physics in the 7th or 8th grade or ninth grade. But for those of you who are not familiar with these equations, I'm going to explain them just now. V is equal to U plus AT is a velocity equation. It tells us what our final speed will be after a given amount of time. If you're told what the initial speed and the acceleration or the rate at which you're speeding up are. For example, if your initial speed is 5 meters per second and you're accelerating at a rate of 10 meters per second square, then your final velocity after 0 seconds will be 5 plus 10 into 0, which is equal to 5. This just is telling us again what our initial conditions are telling us, that the initial velocity is 5 meters per second. So your time, initial velocity at time is equal to 0 is 5 meters per second. Now let's add other times. At 1 second later, 5 plus 10 into 1, which is equal to 15 meters per second you're traveling at. And velocity after 1.5 seconds or 1.5 seconds is 5 plus 10 into 1.5, which is equal to 5 plus 15, which is equal to 20. So simple enough equation, easy enough to use. You can plug in any amount of time that you want, fractions, decimals, as long as it's a real number, and you'll be able to get what the final speed is given your initial speed and your rate of acceleration. Now moving on to the next equation. S is equal to UT plus half AT square is a displacement equation. Now this equation would be absolute child's play if you were not speeding up. If your acceleration was 0, then this reduces to a 7th grader's equation. S is equal to UT, or this displacement is equal to speed into time. For example, if you're moving at 5 meters per second, at your time 0 you have moved a total distance of 5 into 0, which is equal to 0, because obviously you just started, you haven't moved at all. So after 1 second your displacement is 5 into 1, which is equal to 5 meters, and after 2.5 seconds the displacement is 5 into 2.5, which is equal to 12.5 meters. So this will be really stupid and easy to do if you just maintained a constant velocity throughout your travel, but you don't always do that. Sometimes you start at initial velocity of 5 meters per second and during the course you speed up to a final velocity of 55 meters per second. Now you can't plug either of these two into S is equal to speed into time, displacement is equal to speed into time, because which of these two would you plug into speed? Now if you were uniformly accelerating, if you kept the same acceleration throughout, then you can get around this in a convenient way by plugging in your average velocity. Your average velocity is the velocity that is smack in between these two. So your average velocity here will be 5 plus 55 divided by 2, which is equal to 30 meters per second. So now we can plug that in, and your displacement seems to be like 30 meters per second into time. So now we are visualizing the problem not as if you started at 5 slowly and then you sped up to 55, but as if you were traveling the whole time at a constant rate of 30 meters per second. And interestingly enough, it gives us the answer. So it gives us the correct answer, to be more precise. So now let's generalize this. Your average velocity is, if we want to find out a general expression for displacement, saying that we'll put in our average velocity into time. Your average velocity is equal to your initial velocity plus your final velocity divided by 2, smack in between these two, and therefore and we just use the equation v is equal to u plus at. So let's plug in this guy here, and we get average velocity is equal to u plus at divided by 2, and therefore your average velocity is equal to 2u plus at divided by 2. Now let's plug in this guy to s is equal to average velocity into time, and therefore s is equal to 2u plus at divided by 2 into time, and therefore we get down to s is equal to ut plus half at squared. This equation has taken into consideration the speed you were initially moving at, and has also factored in the fact that you were speeding up while you were traveling. So this is a more comprehensive and rigorous explanation of your displacement during your journey. So once again, the two equations that you must be very comfortable with are v is equal to u plus at and s is equal to ut plus half at squared. And if you think about them for a second or two, you'll realize that these aren't really hard. They're two very trivial equations, but from these two trivial equations we will be able to extrapolate all that we need to know about the flight path of this ball. So how are we going to do that? Now we shall proceed by this problem would be a little bit easier if we could visualize the speed of this ball. So why don't we do that? Let us visualize the speed of this ball by assigning a vector to it. A vector is simply a directed arrow. It has a length and it's pointing in one particular direction in space. So the length of our vector when it's representing speed, which is now in vector speech velocity, the length of the arrow is representative of how fast you're going. So if you have a small length, you're not really moving that fast. If you have a large length, you are moving fast. And if you have a length of 0, you don't, the arrow is non-existent, it's not there, then you're not moving at all, right? Secondly, the arrow will point in the direction of the particle at that instant in time. So although the path of this cannonball is curved, at this frozen instant in time the ball is moving in this direction. Now let's carefully watch the animation and see what we can tell about the motion of the ball from the animation. I'm playing now. This arrow is doing two things at the same time. Let me zoom out a little bit. It is doing two things at the same time. It is rotating, for one, that's obvious because its direction is changing, and secondly it is also growing and shrinking. Like, see, when the arrow shoots out from here it's long, but by the time it reaches there it's a little bit shorter. Now both of these can be understood separately. First of all, the change in direction needs no explanation. Obviously the direction is changing while it's traveling through a medium when it's under a force. In this particular case it's under gravitational force. So if you exert any sort of force on something, you can't expect its direction to stay the same. But the growth and shrink of this arrow can be visualized by viewing it as if, okay, view the situation where I chuck the ball directly up. Okay, if I threw a ball directly vertically upwards, what would happen is it would slow down, and then it would speed up again as it comes down. So it would go reach a speed of 0 and then speed up as it comes down. So because of the influence of gravity speeding up and slowing down this ball, the length of the arrow will change. Now, mathematically modeling this arrow is not exactly trivial, and that is so because the arrow is doing these two things at the same time. We can't we'll have to break it up into two simpler pieces before we analyze it further, so that it's not doing this crazy thing of rotating and growing and shrinking. So how are we going to do that? We're going to break this arrow into up into the parts of the arrow that are going up, and the part of the arrow that's going up and the part of the arrow that's going sideways. How are we going to do that? We're going to have to resort to a subject that I found a little bit intimidating while I was in school, called trigonometry. Trigonometry is actually really not that bad once you do a little bit of it. It's just the relationship between the sides of a triangle, of a right angle triangle. It's the relationship between the sides of a right angle triangle given an initial viewing angle of theta. And the sides of a right angle triangle are the hypotenuse. The hypotenuse is always the largest side, and it is the side that's opposite to the right angle. Then from our viewing angle theta, the side that's opposite to our viewing angle will be referred to as the opposite side, and the side that's adjacent to our viewing angle theta will be referred to as the adjacent side. So, and these 6 trigonometric ratios are simply ordered pairs between these 3 sides. You just pick up any of these 3 sides and you make an ordered pair, put one in the numerator, put one in the denominator, and you will get one of these 6 trigonometric ratios. Sine is opposite upon hypotenuse, cos is adjacent upon hypotenuse, and so on and so forth. But for our analysis, we need only sine and cos. Now, the task at hand that we have is, we have this arrow, we're given v, and we're given theta. What we have to do is, we have to break this arrow into 2 simpler arrows. One arrow that's pointing, the part of the arrow that's pointing sideways, which is A, this is V, and the part of the arrow that's pointing upwards, this is B. So how are we going to break up V into both A and B? Now A and B and V conveniently make a right angle triangle, and we know the angle theta, which should be indicative to us that we can use trigonometry. So sine theta is opposite upon hypotenuse, which gives us B by V, and therefore B is equal to V sine theta. Similarly, cos theta is equal to A by V, and therefore, sorry, I'm boxing the wrong equation, and therefore A is equal to V cos theta. 2 simple, short and sweet, beautiful little equations that help us break our velocity into 2 smaller pieces. V has been broken into V cos theta and V sin theta. And now that we have broken our velocity into these smaller, simpler pieces, we can view our velocity in a much more simplified fashion. Wait, one thing I want you to note about the sine and cos functions are that they always lie between 0 and 1. So you'll always get, once you plug in values for this, you'll always get something like half of V, or 3/4 of V, or 1/6 of V. You'll never get anything more than 1 or less than 0. So these 2 pieces will always be smaller than this piece. You'll never get anything larger than V. So anyway, going back to the animation, now we've broken our arrows into 2 simpler arrows that are doing much simpler things. We've broken up into the vertical component that's only growing and shrinking. The blue arrow is only growing and shrinking, and the horizontal component is not even doing either of the two. it's not rotating, it's not growing and shrinking. And this has simplified our analysis to a huge extent. I'll show you how in the next video. See you then.